Howdy. Let's rock and roll, guys. Today is the Earth's interior. So this is kind of an interesting topic we're going to be talking about today. Is how can we get information from deep within the Earth? How do we know what type of rocks are below our feet? Kilometers. Hundreds of kilometers below our feet. How do we know? And we're going to be talking about the branch of science is called geophysics, and it's basically the study of the interior. And we can basically use seismic seismology, and I'll be talking about this. But there's a photograph here showing this is a drill rig structure. I don't know where it's at in particular, but we can drill to a certain depth, and we can basically core and bring up rock samples and specimens and look and identify the rocks and minerals within that sample. So that's one way that we can do it. But the deepest hole, I guess, that we've drilled, it looks like it's 12 kilometers, but it didn't reach the mantle. And everyone knows about the mantle behaves kind of like in a very like kind of plastic. It's kind of very ductile type material. So we're going to talk about this today here. So I've showed this throughout the semester. I've showed what kind of the layers of the Earth, what types of layers they are, and obviously the outermost layer is going to be the brittle crust, and then we get into the upper mantle, which is looks like approximately 670 kilometers. And then we get into the actual mantle layer here. And then this little boundary, the core mantle boundary here, it's showing it as an irregular boundary. It most likely is. And then we get into the outer core. So we know we have a liquid outer core. And then in the inner core, it's solid. And in order for we have a magnetic field that basically shields us from ultraviolet light, and that is created as a result of the liquid outer core. As the Earth is rotating, we generate this electromagnetic field that is created, and it's a dipole. I talked about how it's like has a north and south, and it has the magnetic field lines that emanate from the North and South Pole. So how did we come to realize that we had a liquid outer core and we had an inner core, and how did we understand that? And today I'm going to reveal that to you guys, how we figured this out. So here we figured it out with seismic waves in the interior, and we briefly talked about this. In earthquakes, there's two types of waves. There's the shear wave or secondary wave, and then there's the primary wave. And we remember I talked about that I believe that the shear wave moves perpendicular, and the primary wave moves perpendicular to the body of rock, I believe. So it's just showing you here that the S waves do not travel through liquids, okay, and that the primary waves travel through both liquids and solids. So that's I guess the main thing I want to get at is that the S waves do not travel through liquids, and then the P waves travel through both liquid and solids. So over here, this is important. Here, I want you guys to understand that there's several things it has to do with the rock properties. So one, we're going to have to look at the density of a material, number one, and then R is a measurement of the material's rigidity, and that has to do with the resistance to shear. And then C is the measurement of the material's incompressibility, and that has to do with the resistance to a volume change. So you can think about here, they're showing something that's been packed real tight, and then it was originally, here's this material was originally here, and then we compressed it, and that measurement of whether or not this material is going to basically resist a volume change is the measurement of C. And then R is actually, you have a square, right? And if you apply a stress and you shear this material, that resistance or that pushing back is actually going to be the measurement of R. And then rho, which is the density of the material, it's just showing here a bunch of, basically maybe those are molecules in a body, and they're kind of spread out. And this other here over this shows where they're really packed tight. And that's because it has a greater density. So all of these properties here, basically the properties here reflect the waves. So when we have these two types of waves that actually propagate through a given material, this is, remember, it's showing here that the incompressibility, here it's showing like when that wave goes through this material, it compresses it, and then it expands, and then it compresses. So we can look at different properties of these using these seismic waves, and that's how we've figured out the layers of the Earth. So here's more on evidence from seismic waves. So there's three types of waves here and different properties. So first, they're going to have your seismic wave we talked about is basically the vibrations from a large earthquake. Or you can also, in a seismic surveys, what they do is they bring in an actual truck that generates. You can do it either mechanically. You can generate some type of pulse that'll emanate through a rock body, or you could do it through an explosive detonation, or you can use them naturally. Those are synthetic ones, but would be a natural. Seismic waves are generated from an earthquake. So you're going to have, so when these waves actually are moving through a rock body and they hit different layers that have different properties, what's going to happen is they're going to either reflect. Let me go back. This is just up here. It's just showing you here. It's showing the earthquake. First, a wave is created, and that wave propagates, and then it enters into layer B. Layer B is going to have maybe different properties than layer A, and here it's showing that it does. So this layer is actually going to reflect at that boundary to the actually recording station here. Okay, and then the seismic reflection, which I just went over here. It's just defining that here. And then they also will refract, meaning that they're going to go through the material, but it's going to be basically bent, and that's going to change the velocity at that boundary as well. So here it's just showing this wave is moving through this rock body at X velocity, and then at this boundary, then it is refracted and it has a change in velocity. So from this we can determine. We know that if there's a change in velocity, that there's a different type of rock material there. So here's more on kind of wave refraction. Basically, waves are bent as they enter a medium of different density or different rock properties. So here at this little one, here it's showing V1, velocity 1, I think, and velocity 2. So here's your wave path. And then when it enters this other rock body, it is refracted. So enters less dense medium, slows down, bends away from the boundary surface. And then the other one, it's giving you in retrospect here, it's showing it enters a denser medium, speeds up, and bends toward the boundary surface. And then here, wave enters perpendicular to the boundary and does not bend. So these are three different scenarios that they've discovered or that they found. So what I'll do, I'll stop right here, and then I'll come back shortly, just probably within a few minutes. So I'll talk soon. Hope you guys have a great day.